Welcome to The Explainer. Today, we're going to build a family tree. But surprise, it's not for people. Nope. We're going to map out the surprisingly complex and interconnected family of four-sided shapes we call quadrilaterals. To get us started, let's kick things off with a little puzzle. Think about this. What could a plain old door, a kite dancing around in the wind, and a single cell in a honeycomb possibly have in common? I mean, they seem totally unrelated, but trust me, there's a hidden connection. You guessed it, the answer is geometry. More specifically, they're all applications of the shapes we're exploring today, quadrilaterals. They are, quite literally, the building blocks of the world all around us. So, here's our game plan. We'll start with the most general, basic four-sided shape, and then we'll see how adding just one simple rule at a time creates this whole lineage of more specialized and, honestly, more useful figures. All right, let's dive right in and meet the common ancestor of this entire family, the shape that really started it all. So what makes a quadrilateral? Well, it's actually super simple. It's just any closed shape that has four straight sides. That's it. No other rules apply. But here's the one constant, the one thing you can always count on. No matter how you stretch it or skew it, the four angles inside will always add up to 360 degrees, every single time. Now, this is where it starts to get really interesting. Let's take that basic rule-free quadrilateral and add our very first constraints. And that first rule is all about being parallel. If we require just one pair of opposite sides to be parallel, boom, we get a trapezium. The other two sides can still go off in any direction they want, but this single rule creates our first distinct branch of the family. And we can get even more specific. If we make the non-parallel sides equal in length, we get a special version called an isosceles trapezium. And this shows a key idea for our whole journey. The more rules you add, the more predictable properties a shape gets. Like now its diagonals are equal and its base angles match perfectly. So if one pair of parallel sides gives us a trapezium, what happens if we demand two pairs? This is a huge step because it creates the absolute powerhouse of our family tree, the parallelogram. By making both pairs of opposite sides parallel, we create a much more predictable and stable shape. This is a major ancestor, the parent of so many familiar shapes, because this one rule unlocks a whole host of new consistent properties. And this is where we see the first set of inherited superpowers. Every single parallelogram will have opposite sides that are equal, opposite angles that are equal, and diagonals that perfectly slice each other in half. These are the traits that it's gonna pass down to all of its descendants. Now, from the parallelogram, our family tree really starts to branch out. We can create all sorts of new shapes just by adding more specific rules. First up, let's start messing with the angles. So picture a parallelogram that's kind of leaning over, like a squashed box. What happens if we push it upright, forcing every single corner to become a perfect 90-degree angle? And just like that, we've created a rectangle. It's really just a parallelogram that loves order. It inherits all of the parallelogram's superpowers, but it adds a new one of its own. Its diagonals are now the exact same length. This predictability is why rectangles are everywhere. They stack perfectly with no gaps, which makes them ideal for everything from bricks to books to phone screens. But fixing the angles isn't the only path we can take. Let's hit rewind, go back to our basic parallelogram, and add a different kind of rule instead. This time, we'll just ignore the angles. They can lean however they want. The only new rule is that all four sides have to be the exact same length. This gives us the rhombus, what a lot of us might just call a diamond shape. It's still a parallelogram, so it has all those family traits. But it gets its own unique superpower. Its diagonals now cross each other at a perfect 90-degree angle. And that rigid, perpendicular intersection is why the rhombus shape is so strong, why you see it in things like lattice bridges and those expandable gates. Okay, so we've made one child of the parallelogram that has perfect angles, that's the rectangle, and we've made another that has equal sides, the rhombus. So what do you think happens when we combine them? What if we demand both? We're basically taking the best traits from both parents. We demand the perfect 90-degree angles from the rectangle, and we combine them with the equal side lengths of the rhombus. And when you merge these two sets of rules, you get the final, most specialized and most orderly shape in this entire family. And here it is, the square. It's the only shape that satisfies both of those tough conditions at the same time. All its sides are equal, and all its angles are 90 degrees. And this is the key takeaway. A square isn't just a square. Because its angles are 90 degrees, it's also a rectangle. Because its sides are equal, it's also a rhombus. And because its opposite sides are parallel, it's also a parallelogram. It inherits every single superpower from every ancestor in its family tree. And this family tree, it isn't just some abstract math lesson. It explains why the square, with its ultimate combination of order from the rectangle and equality from the rhombus, is such a stable and reliable foundation for our world. It's in the pixels on this very screen, the windows in our homes, the tiles on our floors. It is the perfect, predictable outcome of a long and very logical geometric history.